So next topic is the much important one. In the previous lectures, where we have discussed the instruction set architecture, then your microarchitecture, and now we are going to talk about the system, system architecture. So there is system architecture. It talks about the architecture talks about the cache design and the memory organization of the system. So in this case, you just follow from the first book, follow the chapter 7.2 and 7.3, and from the second book, follow the appendix B. So most of the content will be taken from these two. And here we are going to talk about the overview of caches and caching basics and the cache performances. Okay. So in the overview of your cache, if you see the performance of your CPU and the memory performance, right from the starting generation of your computers, from 1980s onwards, when it is compared based on Moore's law and this Dennard scaling, using these concepts, the number of transistors are increased or accommodated on microprocessor or CPU to increase the performance of the CPU. So if you see here clearly, by using this Moore's law and Dennard scaling, the performance of your CPU is almost double per every 18 months. In every 18 months, and as the time grows, and by following Moore's law and Dennard scaling law, the performance of microprocessor drastically increased 60% per year, whereas the DRAM performance is increased just 7% per year. As we know that when the CPU is going to perform some operations, it is going to check the requested data is available in the cache memory or not. If it is available, then immediately it will be loaded into CPU to execute that instruction. If not available, then it goes to the main memory. In the main memory, as we know, the size of the main memory is more. So first locating the data in this main memory, and after that take the data here, and then from load here, it takes a lot of time. That during this time, your CPU is always in stall. It stops executing until it gets the data. So that's the reason the processor memory performance, there is a huge gap between CPU and your DRAM that grows 50% over years. So that's the reason there are a lot of CPU design mechanisms, or the cache design mechanisms are required. So the memory hierarchy design in this system architecture, until now we have assumed that a very ideal memory. So all memory access that takes generally one cycle time. In our pipelining, we have seen that example. But in reality, it takes around 100 to 200 cycles. 100 to 200 cycles to complete the memory access time, the memory execution stage, the memory stage in your the pipelining. So assume that an unlimited size is there. That means how it will be affect. Suppose if you have the memory which is having a big size in that memory, and the data is suppose here at some location in this memory, then when try to fetch this this data, in that case it first going to search all the way right from beginning, and after that first it needs to locate. After locating that, it will fetch that one. So in that case, what happens? First locating data, it takes a lot of time. After that, it will fetch. So assume that there is an unlimited size, but if there is an unlimited size in the memory, then the accessing the data It takes a lot of time. If instead of that we use suppose a small memory, in that small memory if this data is placed, then accessing this data will take much lower time. So by keeping this thing in mind, then it says that what is fast memory is very expansive, because by it increase the performance, so definitely it is very expansive. And the unlimited size memory is not that much expansive, but it takes a lot of time to locate the data. So large amount of fast memory would be slow, as said, and the small amount of memory would be faster. So by keeping this thing, there is a trade-off that by keeping two things in mind. One is cost and speed. Cost should be low and speed must be high. At the same time, size should be low and speed must be high. So by keeping this, what is the solution means? Smaller the memory, then it must be faster. When it faster, it costs the more, that is the expansive in the memory, close to the core, and that we call the cache. And larger means it is in nature it is slower, and it's cheaper memory the further way. So by keeping this thing, cache plays an important role. Cache plays an important role. Okay, in that cache is, we call this cache as a type of small and the fast storage which is used to improve the average access time to slow memory. Average access time to the slow memory. So what is the meaning of this one? What is the meaning of this one? That means, the memory, there is a CPU called, that CPU holds the CPU core, we call core. In that core, the cache will be there. In that core, the cache will be there. The cache will have the registers also, right? So what happens from the main memory, the copy of data which is their main memory, that will become and stored in this CPU core. And when it is try to execute, then it will first check in the cache, and if it is available, then that request for this data will not go to this memory access. So that time will be saved. So as said, the cache is a type of small fast storage which is used to improve the average access time to slow memory. That plays an important role between your core CPU and your memory. So what it do? Cache can simply hold a copy of the subset. A copy of the subset. That means whatever the data is there in the main memory, from that main memory, suppose it is going to load a data A, then in the cache memory, it will just use the copy of this data. The copy of this data will be stored here, call this copy. Okay, but the actual data will be there in the main memory itself. So because it is just holding a subset of your main memory. Okay, subset of the main memory, the instruction or data which is used by the program. So to exploit the special and your temporal locality, before doing that, you just see the hierarchy of these memories. See the hierarchy of these memories. The smallest unit which is used to store the operands of any operation, that use the registers. So registers are typically your 32-bit registers. So we call your 4-byte or 4-byte registers. So then another memory which is little bit bigger than your register, we call that as your cache memories. So this cache memory further divided into L1 cache, L2 cache, and L3 cache. L1, L2, and L3 cache. So how they are, looks like means on your CPU, in the core CPU, the registers will be there in the core CPU. The registers will be there in the core CPU. Okay, so whenever CPU performs any operation, it will go and check whether the operands are available in this register or not. If not, then there is another little bit bigger than your R, no, the registers. We call them as your L1 caches. L1 cache, which is closer to your core or on the die of your core itself. Okay, that hardly takes the 5 cycles to load the data. If the data is not there, then another cache is there, which is little bit bigger in size, storage size, called your L2 cache. That L2 cache, generally takes around your 10 cycles. It takes around 10 cycles. And another memory which is called the L3 cache, which is bit far away from your core and actually on the edge of the die of your core, that is your L3 cache. It takes around more than your 10 to 20 cycles to load the data. And finally, it will get the L4 caches. This L4 caches, generally we used to say that your DRAM or your the DRAMs which is out of your die core of your cache. I mean the core. So in caching is everywhere in the computer architecture. So in computer architecture, almost everything is a cache. So the registers are a cache on variables or the operands for software management managed, and the first level cache, that is your L1 cache, is on the second level cache, your L2 cache, and the second level cache, your L2 cache, is on the cache of your memory, that is your L3. And then we find the memory, a cache on the disk we call the virtual memory. And apart from this, there is a translation look-aside buffer cache is there that we call the page tables. And apart from these two, there is another temporary caches are there. We call them as your branch target buffers, and this branch target buffer caches on the branch that holds the branch target, which we have seen the hardware implementation of this branch target buffer. So what are the common cache hierarchy? As we just saw in the previous diagram, that the most processors today have three levels of caches. As I said, that L1 cache, L2 cache, and your L3 cache. So one major design constraint for this cache is their physical size, on the CPU die. That is what we have seen just now. There is a CPU core. In CPU core, registers are there, and then the L1 cache, which is smaller in size but bigger than your registers. Then L2 cache, which is smaller in size but bigger than L1, and L3 cache, which is smaller in size and faster but bigger than your L2. So because of their because of their size, physical size on the CPU die, they are limited by their sizes. So we cannot have too many caches. On one, CPU. So some high performance and are the embedded processors. They have the L4 caches also, that we call them as your DRAM cells instead of the static RAM cells. So what is the use of this L1 caches means? The L1 caches are very closest to the CPU computation logics. They are very close to your CPU computation logics like your ALU, arithmetic and logic units. And to avoid the pipeline structural hazard, we have seen in our example in the pipelining that this L1 cache is divided into two parts. One is the instruction cache, another one is your data cache. So L1 caches are usually partitioned for your data cache, that is D cache, and instruction cache. So generally the size of this L1 cache is at most 64 kilobytes. So these 64 kilobytes are divided into 32 kilobytes for your data and 32 L1 cache your L1 cache 32 kilobytes for your instruction storage, for your instruction. So these L1 caches are mostly, as bigger caches are too slow to access and will be physically too far away from these computational logics. Then L2 caches, these L2 caches are slightly further away from your CPU, as we saw. They are slightly away from the CPU. So register your L1 and then your L2 caches from the CPU, core CPU. Thus, L2 caches are slower than your L1 caches, but have the larger storage space compared to your L1. So typically, L2 caches are 256 kilobytes in size, the unified for both the data and the instructions. And then comes to your L3 caches. These L3 caches are the largest caches and typically aim at holding all of your working set in it. That means to hold the complete program. And these L3 caches are usually are located outside the CPU. Outside the CPU, they will located it outside the CPU physical die or CPU core die due to its bulky storage. So if you see this example of your Skylake dual core processor, there are two cores are there, CPU 1 and suppose CPU 2. In these cores, they are made up of your transistors. So these transistors, they are the L3 caches. The L3 caches are outside the die of your CPU core, whereas your registers and L1 caches are on the CPU core. Apart from that, there is a system agent is there which are used to these units are functional units are known as your memory management. Memory management, the memory management units, the memory management units, and on the memory controller you'll find the display of your input output controllers. So here, if you go and check inside the CPU core, as we said, there is an execution unit like your ALU type. Then in this execution unit, your L1 caches are bit away from your execution unit, and that is your L1 cache is divided into two types: L1 data cache, another one is your L1 your instruction cache. Once the L1 instruction cache is having some data, then there is another unit which is used to decode that instruction, and that decoded instruction supplied to the execution unit. And in that, for that, the execution unit for that instruction, it requires data, so that data will be retrieved from your L1 cache. And there will be for executing the out of order instructions. So there is a special units called your out of order scheduling retirement units. And if you see from this diagram, then there is a LT cache which is a little bit bigger than your L1 caches in size. They are a bit away from this execution unit. They are a bit away from this execution unit, and the L3 caches are completely at the outer die, the physically outer die of your core. There you can find the L3 caches. So this slide is very important for your assignment purpose also. The memory hierarchy space, as said, typically the registers, they hold the capacity of the registers are typically less than 2 kilobytes, less than or equal to 2 kilobytes, and these registers are on core only. So the latency to access the operands from these registers, it takes only 1 nanosecond. 1 nanosecond. Similarly, the L1 cache, in terms of its capacity, it's 64 kilobytes. 64 kilobytes. Out of that, 32 kilobytes for holding the data, 32 kilobytes for holding the instruction, and its latency, it takes at most 4 nanoseconds. It takes at most 4 nanoseconds. And the another cache, L2 cache, which is, if you see in this capacity, as the capacity is increased, their latency time is also increased to locate the data and load into the CPU. The latency time is also increased. For L2 cache, it is at the size of your less than the 8 MB, but L2 caches generally they use is 256 kilobytes of each one. And then comes to your L3 caches, that is in the size of your 64 megabytes, and then from the it takes 20 nanoseconds time. It takes 20 nanoseconds time, and then comes to the L4 caches. We call the main memory. We call that is your main memory. It is generally in a simple computers they may use the main memory like 4 GB per rank, but it may be as the computer requirement increase, then it goes from 8 GB to your 8 GB to 16 GB to 32 GB, 32 GB. But as the modern computers for the research purpose and as they use these main memory from 128 from hundreds of GB to some tera GB also. Hundreds of GB to some tera GB of RAM is used for that. So in those memories, it takes around 100 nanoseconds. 100 nanoseconds. 100 nanoseconds. And the other than that, the hard disk we used to say the secondary memory, we call them as SSD or HDD. They are greater than 1 GB in size, and up to what you call the some tera GBs also. There it takes the 5 milliseconds to your 10 milliseconds time. So this latency, along with this latency, what is the approximate bandwidth means? For registers, it is 150 gigabytes per second. For L1 cache, it is 100. For L2 cache, it is 50. For L3 caches, it is 32 GB. For memories, it is 10 GB. So as the memory size is increased, the bandwidth is decreasing. The bandwidth is decreasing to completely transfer the selected data from main memory to your CPU or CPU to the main memory. So this is the memory hierarchy spaces and its latencies. So then comes to your program locality. Program locality is why the caches are works. In program locality, why the caches are works. So let us consider a simple example for this program locality. Let us say if you have a program, we have the program. In that program, you are having some instruction. I have one instruction where R1 is used to store the address of your A. Then some instructions are there. Then another instruction that is move, and that stores the address of your A, the R2 register. So in this, how these caches are increase the performance of your CPU. Let us see that. Okay, first let us see without cache, what is the how much time it takes, and with cache how much time it takes. Let us see. Okay, so generally what happens in this case, in the execution of that, you will have this CPU. The CPU will request the data to execute this move instruction. First, it will send a request. It requests that instruction which is to be executed in the memory, because in the first case without cache, if it is the main memory, in that case in the main memory, it will be located somewhere in the main memory. The A is located somewhere in the main memory, and once this CPU requests this instruction to execute, it requires this operand. Once this is located and send it back to your CPU, it generally takes from your previous case from main memory to when CPU is requested, when it gives load back to the CPU, it takes generally 100 nanoseconds. It takes 100 nanoseconds. 100 nanoseconds. So the for first instruction to load this data from your main memory to CPU, it takes 100 nanoseconds. Similarly, for the second time also, the same variable is used. Okay, and that A is available in the main memory. So from this main memory, it is locating this A and then fetching and load into your CPU is again it takes the 100 nanoseconds. 100 nanoseconds. So how much time it is taking? The total time, latency time, the total latency time it is taken is 200 nanoseconds. 200 nanoseconds in this case. Okay. Now let us see with the cache. Let us see with the help of the cache, how it performs. So we have CPU. Now CPU requesting that instruction A, send the request to the cache, but it is not there in the cache. So obviously it goes to check whether the data is available in the memory or not. So if the data A is available in the memory, then first what it will do, it will load that data into your cache. Load the data into your cache. One copy load into cache, and then it load into the CPU. So total time which it takes, so from again the first case is same. It is take for the first instruction to execute. It is accessing that data from your memory. So it takes 100 nanoseconds. So it takes 100 nanoseconds. But in the second time when it is executing, your CPU send that request to your cache. The cache is having one copy, so it is simply sent back to or load to your CPU. Your load to CPU. So if this cache is suppose L1, L2 cache, it takes suppose 10 seconds, 10 nanoseconds. 10 nanoseconds. So second time it takes 10 nanoseconds. So total you will get the 100 nanoseconds. So from it, it is very clear that to improve the performance of your CPU, it should maintain it should have the caches so that the data which is frequently used, or the data which is reused will be readily available in the cache memory. So in our case, the A which is using here and A which is using here, it is this A is reused, right? So when this A is reused, all the reused data will be available in the cache so that it will increase the performance of your CPU. So from this concept, we can derive that what is the program locality. So in this program locality, the memory hierarchy exploits the program locality. So the programs tended to reference parts. Reference means here the memory address or memory address of your data. The memory parts of their address space that are local in time, in terms of the local in time, that how much time it is taking, local in time, and the spatial. So that there are two types of program locality. We call the temporal locality and spatial locality. So this temporal locality recently referenced addresses in our example, it is A, which are likely to be referenced again and again, are reused. So that will be what we call that as your temporal locality of the program. And another one, your spatial locality of a program. In spatial locality, if we have the array, suppose if I have the array of 5 elements, then these 5 elements are going to be arranged in the array that 1, 2, 3, 4, and 5. So when the first element is accessed, then it will assume that the the next element in that array will be, next element which is closer to the first one will also be accessed, and the next element, the third element, when second element is accessed and used, then it will assume that the third element will also be accessed. Similarly, the third element is accessed means next to third is fourth element will also be accessed. So this part we call the, if an address is referenced and then nearby addresses are also likely to be referenced soon. So this we called as was special locality, special locality. But for some programs, this program locality will not work. For some programs, for example, if you have the machine learning application, typically they use the very low data in the locality because the data is very huge, so they always access from the memory only, not from the caches. So these programs are called your streaming programs, and they are the main focus of today's, the system, the researchers. So this is another example for your locality. So consider this program. In this program, there are two variables are there which are are declared here, initialized, and after that, in this for loop, there is one variable I, and then once it is initialized, then it entered into the loop body, and then it add the value j into the element of your array ai, and a bi element with your k. So from this, if you see that the data locality of this program, if you see that the data locality is I, capital A, capital B, J, and K. These are the data which are the data locality. In that, your I is reused and updated for all the iterations in this case. Okay. Hence, this is a temporary local, as well as your J and K, they are also reusing. J and K, they are also reused and stay constant for all the iterations. So hence they are also temporal local. And comes to your A and B. A and B, these arrays, A and B, that is, if A of I and B of I is accessed, then if A of I plus 1 in the next iteration, A of I plus 1 and B of I plus 1 will soon be accessed. Hence, they comes into our special locality. Generally, in special locality means it is, if any arrays are there in the program, that comes under your special locality. So apart from this, there are the instruction locality also. So in that instruction locality, what is the some from this, what is happening first, it is moving the values into your j. So move instruction will be executed, then along with move this value 1 is assigned to j, value 2 is assigned to k, then 0 assigned to 1. So move instruction is executed, and next in this loop it is going to add the increment, auto increment is there. So add instruction is also every time executed in this iteration, and then this is complete, then every time it is going to comparing. So the comparing whether it is I is less than your 10,000 or not. So comparison, your compare instruction is also executed again, and once it is finished, then it is going back to execute the same, means target address is there. So your jump instruction is also there. So these instructions are also there. These instructions are also continuously executing. So we call that instruction locality. So some loop body is executed over all iterations. So hence they are the temporal in the local. So then comes to, there are some terminologies which are used in these caches are the lower level in the hierarchy are closer to your CPU, as we just discussed that L1 caches are right outside your CPU, and L2 caches are usually surrounded the CPU core, and L3 caches are usually located outside the physical die of your CPU core. That is what we have seen in the diagram pictures. Okay, so that we call the uncore part of your L3 is uncore part of your CPU, whereas L1 and L2 are core part of your CPU. So at each level, a block is the minimum amount. A block is a minimum amount of data whose presence is checked at each level, whose presence is checked at each level. Okay, that means what? Let us see this, that if I have the memory, in this memory, how it is assigned means, let us just discover what is the block of this one. If this memory size is suppose 1 megabyte of memory, this 1 megabyte of memory is arranged in number of rows and number of columns. In this, every cell, we call it as your block. We call this as your the block. So generally the size of this block is 64. The size of this block is 64 bytes. 64 bytes. Similarly, next block, it's also size of your 64 bytes, 64 bytes, 64 bytes, and so on. So this 1 MB of your memory, main memory, suppose for our example, if this 1 MB of memory is there, means how many blocks are there in this 1 MB of memory, means it generates 1 MB divided by each block size is 64 the bytes, then it will generate the 16k blocks. That is, it is approximately 16384 blocks. So this block is a minimum amount of data whose presence is checked at each level. Means what? The blocks are of, sometimes these blocks are often called the cache lines. Cache lines are simply lines. So the block size is always the power of 2. It is always the power of 2. So contemporary processors are usually having the cache line of size even 64 bytes. 64 bytes. So what is the meaning of this? The block is the minimum amount of data whose presence is checked, means generally we are, as we saw in the previous the example, when CPU is going to execute the instructions, then first it is going to request to access the data in the cache. Okay, if it is not there in the cache, then from there the request forwarded to your main memory. Okay, so from this main memory, this is the main memory. From this, suppose if it wants to load the integer a, suppose that integer a is somewhere in this block in the main memory, that is not available in the cache. So that a which is there in the main memory, it will be located, and that located one sent back to your cache. So cache will keep one copy of that a and then load into your CPU for the execution. So for the next time, in our previous example, we are saying for the next time, when that the move instruction of your R2 and A, in our previous example, that R2 and your A, next time when it is reusing, it will first check inside the cache. So that is the minimum amount of data whose presence is checked at each level, if it is there or not in the L1 cache. If it is not there in the L1 cache, then it goes and check in L2 cache. If it is not there in L2 cache, then it will go and check in the L3 cache and then in memory. So this process is continuous. Okay, this is another the terminology. So then comes to this some other terminologies are the references is set to hit at a particular level if the cache line is found at that level. So if you see this, when CPU requesting a data for execution, and it will just go and check in the cache, if the requested data, which in our example, which is A, is available, then we call it as your hit. If the CPU is requesting the data A for the execution purpose in the cache, and but it is not there in the cache, suppose, then we call it as your miss. Okay, so then the what is the hit rate and your the miss rate means, if there are CPU is, suppose, for example, nine times the CPU is requesting to check whether those 9 times the addresses for the instruction which are available in the cache or not. If they are available, it gives out of 9 times, suppose first 5 times the A's are not available, suppose missing, and next 4 times if it is the hit is there available in the cache, then from this observation the hit rates and the miss rates will be calculated. Hit rate is the number of hits divided by the number of addresses which are requested by your CPU. Number of addresses, we call them as references. Same way for your miss rates also. Same way for your miss or miss references also. So the access time of a hit is the hit time. So access time means when the CPU is requested a data address, requested a address, the cache, then the cache will go and locate this data, and then send it back to your CPU. We call that as your access time. Locating the data and send it back to the response time, send it back to your CPU, we call that your access time. So that access time of your hit means your hit time, we call it as hit time. So the additional time to fetch, sometimes if the data is not there in the cache, then it will, that request go on forwarding to the your memory access. From the memory access it will locate this A, and that if the data is not there, we call that as miss penalty. So what is this miss penalty? The additional time to fetch a block on a miss is called the miss penalty. So to locate A here and send it back to your cache, and will then the cache will store this time from memory to your the cache load or response time, we call the miss penalty. So if there is a cache miss, then data has to be fetched from the higher level of caches. If it is not there in L1 cache, then it go and access in L2 cache. If it is not there in L2 cache, then go and access in L3 cache. If not there in L3 cache, go and access in L4 cache. That is your DRAMs. If not there in DRAM, then it goes and access in the HDD, the hard disk. So if the cache miss, happens at the X level, then the data will be fetched from the caches with the levels larger than the previous one. So this is the hit rate and your miss rate. So then comes to the terminologies. We call the miss penalty. As we said, miss penalty means the access time which comes from your CPU. From CPU, it is just checking in the cache. It is not there in the cache, so it is going to main memory. So in the main memory, first it is finding the access time, that locating the value, and after locating, when it is sending back, that is, we call this as your transfer time. So this miss penalty is equal to access time plus transfer time. Okay, so this transfer time is a function of your bandwidth. The time for all the blocks to get back from this main memory to your cache. That means if the cache size is increased, suppose cache size is increased, okay, the bandwidth, if the bandwidth is smaller one and cache size is increased, then it will affect on the the transfer time from the cache size to your cache size, will affect the transfer time based on the bandwidth. And your access time means the time for memory to get request and process it. As said, get request and locate the value and return it back, that we call the access time. Okay, so this access time is typically constant, and while the transfer time is depends on the size of your cache line. So the access time that not depends on the block size, it is constant, but as block size increase, then the transfer time is also increased. Transfer time is also increased. If bandwidth is bigger, suppose bandwidth is bigger, then it is simply the complete block can be your block can be at a time it can be transferred, but if this bandwidth is smaller, then this block will be divided, and b1 block 1 will be transferred first, then block 2 will be transferred next. So that will increase the that transfer time is depends on the bandwidth of that. Yeah, so this access time versus the transfer time, which we just discussed. So this access time is from this diagram. This main memory and cache. Access time is the time of your request transfer to main memory, and processing this time is your access time. And transfer time, once it is identified when you're transferring it back to your cache line, that takes your transfer time. Then your miss penalty is calculated as your access time plus your transfer time. That is total time taken from your cache to memory, memory to your cache, that we call the cache miss penalty. Cache miss penalty time. Cache miss penalty time. So in this latency and bandwidth means latency is just time is about the time for completing one task. As we said, just going sending the request, locating it, and sending it back to the completing that task, sending it back. So that we call the latency is about the time for completing one task. But bandwidth is about, suppose if I have a cache here, okay, suppose cache is there and the memory is there. So then one request is given. So that request is processed. I mean that request is transferred and processed and go back to your what you call to the cache. Generally takes 100 nanoseconds, right? Like that, if there are 4 requests are there, suppose if there are 4 requests are there, then in that case the bandwidth says that there are 4 requests per 100 nanoseconds, that we call as your bandwidth. So bandwidth is about the number of tasks that can be done within a time, whereas your latency is a time which is taken to process and send the response back. Okay, so this bandwidth can be increased by simply having more the workers working on a multiple tasks simultaneously, or bandwidth is equally affected by the latency and parallelism. So with this memory for this bandwidth, how can it be improved means wider buses can be used instead of narrow buses. You can use the wider buses, okay, or large block size and more DRAM channels. But latency is very hard, or very harder, or still much harder to improve this latency. That is how to get a request from the cache to memory. How to get a request from cache to memory. Then comes to the caching basics. In this caching basics, if you see this, the caching basics, let us it comes to when try to designing this basics, it comes the most basic questions that how do we know if a piece of data in the cache is there or not? Because as we know that in instruction fetching, the memory from this memory the instructions which are there in this memory, they will be fetched and stored into your cache, in the cache, okay, in that cache. Then it will check whether how do we know that the piece of data which is requested by your CPU is there in this cache or not? How do we know that? How do we know that? If a piece of data, suppose if a piece of data is available, suppose here, then how do we find it? In which location in this cache the data is there? How do you find it? Or if it is not there, then what to do? How to go to your memory and fetch that one? That is, if it is not there, then how do we get it? So from this, there are more detailed questions comes. We call there are 4 questions which comes into the cache design part. First is cache line placement policy. Cache line placement policy means where does a cache line go? If that cache, the CPU requested, send a request to your cache. If that in that cache, that memory is suppose if it is not there, then the request will be forwarded to your memory. From that memory, if the cache, if the data is identified, that will be fetched and stored into the cache. But where it should go and take place, whether it is in the first place, next place, where it go, that is the placement policy. Where does a cache line go when it is fetched from the memory? Second, once if it is stored in this cache, suppose, then how to identify that cache line? How to identify, suppose if A is here, suppose, go and store here, then how to identify this cache line from this many numbers? So this cache line replacement policy, no then once if this cache is full, suppose if it is stored with all the data from D, and if it is requested, suppose E data, then where it should go and take place? There should be a replacement policy, right? And along with that, another question is your write strategy. Write strategy. Does any of this defers to read or write in the cache? So these are four questions. Comes to design this. So we'll see this. The general view of a cache, when we talk about this caches, the cache is an array of memory. The cache is an array of memory. As we said, if it is a main memory, then in the main memory that is divided into the rows and columns, everything we call as your block one, or sometimes we call this as your cache line also, or simply we call the line also. So when this data from this block or cache line is fetched from this memory, it goes and stored in the cache, So what is this cache means? The cache is defined as the structure as it consists of the cache it consists of frames. So the frame is having three fields. One is your data field where the data which is fetching from these blocks, that will go and store in this data field. Second bit is whether this data is valid or not, that we call the status bit. Okay, and if that data which is there in the cache is valid or not, then at what address that data is stored, we call as your tag. So tag is nothing but your address. So this is the structure of the cache. Cache is the made up of your frames. That frames consists of your data, tag, and your state bits. Okay, this tag is simply a memory address of your cache. What is the address of this? Suppose the address of the cache frames, like address 100.0.0.4.1.0.0.8, like that. The address of we call this as your tag. Okay, then state bits are valid bits that has valid data in the frame or not, and the data bits, that means if they are not valid data, then it will be write backs. So this cache line, to do this in this caching mechanism, there is an algorithm we call the cache line matching algorithm. So in this cache line matching algorithm, whenever there is a CPU request, that request is having the address of the cache line. Cache line address will be there in that request. So from that cache line, it is going to find whether the frame is there or not in the cache. So that is find a frame. So how it is going to find a frame means, in that cache line, whatever the tag is there, when this address, this tag is there in the cache. When this cache line is coming, then the incoming, this cache line also have the tag address. So if the incoming tag is not stored in the if it is there, suppose if it is incoming tag is equal to your stored tag, then it can simply fetch, there will be a hit here, because the as we say that CPU requested, and that is matching in the cache. If it is there, that means it is a hit. If it is not there, if this tag and the stored tag and the incoming tag, if they are not equal, then the cache miss occurs. So then the evict the cache line currently in the frame, evict these cache lines currently in these frames, and accommodate uh, the read request data from your memory and higher level of caches, and then replace the cache line read from the memory at the higher level of your caches, higher level of caches, and then it return the appropriate word within the cache line, within the cache line from this part. Okay, so let us see this with an example, but we'll try to discuss this example in the next class. The cache line example. So this I would like to just stop the session.